Hello and welcome. This is again Guido from the company The House of Medici Corporation. In this video, I'm going to demonstrate how you can perform summation on quantum computing by using IBM's real quantum computer. For those of you that have been watching some of my other videos, you may know that I've already produced a general introduction where I showed you how to perform basic operations on a quantum computer. So my roadmap is that I will lay the foundation for quantum computing with a series of videos, and by doing so we progress towards the state-of-the-art, more difficult algorithms such as Grovers and Shors. This video, by the way, is based on an article that I published in Medium and read it some time ago. For this video, we will be using IBM's quantum computer in order to show the magic of the quantum Fourier transformation, and we will be using Qiskit, IBM's quantum computing language. If you don't know what the Qiskit is, you should check out either one of videos or go directly to the website of IBM. Qiskit is an open-source quantum computing software development framework provided by IBM. It allows researchers, developers, and enthusiasts to write and run quantum computing algorithms on actual quantum machines through IBM's cloud services, as well as on simulated quantum computers. Here are some key aspects of Qiskit. Qiskit is composed of several components that cater to different aspects of quantum computing. There is Qiskit Terra. This is the foundational part of the framework, providing the tools to design, optimize, and execute quantum circuits on various backends, hardware and simulators. Then there is Qiskit Air. It focuses on high-performance quantum simulation to predict and verify outcomes. And then we have Qiskit Ignis. This one deals with quantum hardware error and noise characterization, offering tools for error correction. Finally, there is Qiskit Aqua. It provides higher-level tools to build algorithms for quantum applications, such as chemistry, optimization, and finance. Qiskit is primarily written in Python, making it accessible and easy to integrate with existing Python libraries and frameworks. It allows users to construct quantum circuits using a simple Python interface. So Python being the basis of Qiskit is a wonderful thing, as it will enable us to take advantage of the large Python libraries for computing and artificial intelligence. Let's start with Anaconda in the Jupyter Notebook, and let's start importing some stuff that we need for our operation. Once we've imported everything that we need, let's discuss what we actually want to do. So in a nutshell, what we want to do is we want to add up two numbers. Let's start with two numbers. Let a be an integer, and let b be an integer. Let s assign values to a and b. A shall be 1, and b shall be 2. And so now what we want to do is we want to obtain the summation of a plus b. That would be 3. And so this has been calculated on our CPU, on our classical CPU. Now what we intend to do is the same thing on the quantum computer. And so the first thing we have to do is we have to find a way how we actually get those numbers onto the quantum computer. And what I'm going to do is I'm going to basically encode the number A and the number B on two separate circuits of the quantum computer. And so let's start off by first creating a quantum circuit. Alright, so this is what our quantum circuit looks like. So we have here 6 qubits. So qubit A, qubit A, qubit A, and the same with B, and then we have here a register called C, which is where we will write our results to. So once the quantum computer has calculated everything, it will put it to C. So now what we need to do is we need to encode this number A and B into qubits of the quantum computer. And that is a pretty simple process. You should recall that basically our numbers represented by A and B can be translated into binary numbers, which then looks like this. So here you can see what happens. Our number A, which is 001, in binary it would be represented as well as 1. And our number B in binary would be 010. And so you can put here any number you want. This is basically we can translate our numbers here into a 3-digit long binary number. What we now need to do is we need to encode this binary here into the quantum computer. And so on the quantum computer, every qubit initially starts off in a state. All that's required is to flip the correct qubits. Then, upon reading it out, you'll observe how we can straightforwardly encode the binary number. Flipping the qubit is achieved by using what's known as an X gate. Let me show you what I'm referring to. Now, this is how the circuit appears. The number has been encoded onto the quantum register A, integral to the entire circuit. Let's verify by measuring if we indeed recover it. Let's proceed and check. I've executed this small program on a quantum computer simulator, running it multiple times, achieving consistent results each time. Thus, we successfully input numbers into the quantum computer. Now, I aim to encode numbers A and B in this manner on the quantum computer. I have crafted a function to handle any type of number generally. So here is the function set input state. It accepts the numbers A and B, converting them into binary as previously demonstrated. It then establishes a quantum circuit and converts both input numbers into binary. We then flip the qubit where the binary number has a 1, using the so-called poly-X gate, switching the qubit from one state to another, from one state to another and back. We then restore everything. Currently, I have run it with 2 numbers, measured them, and then illustrated the circuit. Here's what it is. I'm primarily measuring number B now, the second number, and you can see the outcome here. Indeed, it is represented in binary. This digit represents 2, this one represents 1, and together, plus yields 3. Thus, the sum is 3. Now, the next step is as follows. Let's eliminate the measurements. In the next step that we are going to perform, I plan to sum the numbers encoded on the quantum computer and subsequently measure to obtain the outcome. First, we must comprehend the Fourier transformation. Thoroughly explaining the Fourier transformation would take an entire video or more. Fourier functions and Fourier transformations are one of the basic concepts in higher mathematics for engineers, with a wide range of applications. I highly recommend checking out several YouTube videos on this topic, or to simply refer to your university textbooks. From a broad perspective, consider being given a sound wave and needing to identify its component frequencies. The Fourier transformation is the process that enables this dissection. It converts from real space to frequency space. Why is this significant? Well, there's a useful property known as linearity, which indicates that the sum of the Fourier transforms of 2 signals is equivalent to the Fourier transform of their sum. Performing sums in frequency space proves simpler than in real space. The Fourier transform is a mathematical technique that decomposes a function or a dataset, often a time-based signal, into a different domain, the frequency domain. Essentially, it transforms the data to show the different frequencies, and their intensities, that make up the original signal. Here's how it works and why it's useful. First, conversion to frequency domain. The Fourier transform takes a time domain signal, which is a representation of signal amplitude over time, and converts it into a frequency domain signal. It separates the signal into its constituent frequencies, showing how much of each frequency is present in the original signal. Second, mathematical basis. Mathematically, the Fourier transform of a continuous time domain signal that represents the signal in the complex number frequency domain. Third, the inverse Fourier transform. This is used to convert the data back from the frequency domain to the time domain, reconstructing the original signal from its frequency components. Fourth, some applications are audio processing, to analyze the frequency components in music or speech; image processing, to filter out noise or enhance features in images; telecommunications, for signal transmission where encoding and decoding signals are essential for efficient communication; medical imaging, in technology such as MRI, where Fourier transforms help to construct the images from the raw data collected; and of course we can use it in quantum computing to generate basic mathematical operations. The diagram in the image, if it shows a series of peaks, each peak represents a frequency component of the original signal, where the height of each peak indicates the amplitude, or strength, of that frequency in the original signal. This is crucial for understanding the makeup of signals in various fields of science and engineering. There's also a quantum version of the Fourier transformation, well documented in the Qiskit materials, where the quantum circuit used is thoroughly outlined. Fortunately, we don't need to program a quantum Fourier transformation ourselves. It can be imported and used directly as a black box function. Now, having imported the quantum Fourier transformation, labeled here as QFT, we will apply it to the first number, converting number A into Fourier space to simplify the addition process. As you can see, our quantum Fourier transformation box transforms number A into frequency space. I've attached it using this append method. Considering a QFT of 3 qubits, as we're encoding the number in 3 qubits, number A the swap false essentially means that typically in a quantum Fourier transformation, qubits are interchanged. However, I will manually handle this and avoid using swap gates, which introduce errors. To maintain minimal errors in our program, we simply specify which qubits the transformation should be applied to. Once in Fourier space, adding numbers becomes straightforward. To understand this, I will consult the Qiskit documentation, where it is described in detail. The Qiskit documentation clearly explains the quantum Fourier transformation, stating that it transitions between the computational and Fourier bases. Crucially, this section discusses counting in the Fourier basis. As I mentioned earlier, when we initially encoded our number, we represented the numbers as binary strings and flipped the qubits accordingly. You can see this reflected in how qubits are flipped. With 0, all are up. With 1, this one is down. And with 2, only this one is down, and so forth, demonstrating how counting occurs in the computational basis. In the Fourier basis, counting changes slightly after the transformation. Numbers are now incremented using various rotations on each qubit. For instance, on qubit 3, there's a rotation of pi. On qubit 2, a rotation of half pi, and so forth. Thus, we can count by applying these rotations instead of flipping the qubits fully. You'll see in our notebook how this method simplifies addition. Now, I will write the function to perform this task and explain its workings afterward. Writing this function seems more straightforward. Here's the function, and now I'll place it there and later describe its function. Let me now clarify what I've implemented. This function I've designed performs the rotations demonstrated in the documentation, applied based on our second number. Essentially, the concept is this: if there's a 1 at our number B position, indicated by an X gate, meaning the qubit was flipped and a 1 is present, you'll notice a connecting line labeled control. Control implies that if this qubit is a 1, a rotation of pi over 4 will occur on this qubit of A. Thus, we're adding up and counting on this qubit. The function computes all potential combinations, and whenever it finds a 1 in the B subcircuit, it increments the corresponding qubits in the A subcircuit, facilitating addition in Fourier space. Now, all that remains is to revert to real space. We simply perform an inverse of the quantum Fourier transformation, obtaining our outcome and completing our summation. I've now added the inverse quantum Fourier transformation and also set up the measurements, tidying up the setup slightly. Our numbers are 1 and 3, and we're summing them. Initially, we set the input state, then perform the Fourier transformation, sum in Fourier space, and finally, reverse the transformation. I've executed this on the simulator, and as you can see, we obtained our outcome. We ran it 100 times, measuring each time on the simulator, achieving the correct result, which you're already familiar with if you know binary. Let's quickly verify. Indeed, the result is 3. Adding 1 and 2 yields 3. Now, the only remaining step is to run this program on an actual quantum computer from IBM. So, the first action is to switch our backend. Now, we only need to select the quantum computer we wish to use. I'll try it over to the IBM Quantum Experience. We are utilizing 6 qubits in total. Let's determine which machine is available. The suitable machine is in Melbourne, equipped with qubits. All other machines have 5. I'll opt for the Melbourne machine. Let's copy its name and paste it here, then initiate the program and see if the quantum computer can handle the addition. Let's find out. Here's a result. These are all different outcomes. We measured times, displaying the probabilities of each. For instance, we achieved times, illustrating the likelihood of that result. What's evident here is that we receive a random outcome. We merely encounter noise. This indicates the quantum errors at play. We couldn't sum the 2 numbers on the quantum computer. The errors were too significant. I'll now attempt to reduce the number of qubits we're using from 6 to 4 to fit on smaller quantum computers with fewer errors. I believe this will allow the program to run correctly. You can see I've reduced the qubit count. We're now adding 1 and 2. The expected result is 3, using only 4 qubits. If we visit the IBM Quantum Experience, more machines are now available. I'll select the IBM Santiago machine, which has 5 qubits and a high quantum volume, suggesting lower error rates. I anticipate this machine will successfully execute the program. Let's see. The program is now queued. If you check the IBM Quantum Experience and refresh the page, you'll notice we have a job queued. Let's observe. Here's our job, currently queued and expected to run in 3 minutes. Let's wait and see if the outcome is favorable. We've received our result. You can see we were in the queue for 1 minute and 1.5 minutes, with a runtime of seconds. Here's the result, which looks much better. For those familiar with binary, you'll recognize that 1 and 1 in binary is indeed 3. We achieved the correct result with a confidence of %. The remaining discrepancies are errors. now significantly reduced as the smaller devices perform better than the previously used larger qubit device. To confirm, the notebook shows the same result. The final step is to demonstrate that indeed 1 and 1 is 3 in binary. Yes, we managed to sum our numbers. We calculated this on a real quantum computer from IBM. So, you've just witnessed how numbers can be summed on a quantum computer. Clearly, conducting such operations on a quantum computer is currently impractical. This early stage of the technology highlights that many tasks remain beyond the capability of today's quantum computers. The field is rife with expectations, and this truly reflects what can realistically be achieved at present. People familiar with our company may know that other areas of quantum computing are far more advanced, and we are looking forward to the first practical applications. Thank you for your attention. I hope you found this video informative, although it is more technical than usual. Let me know in the comments if you'd like more videos like this. Please like the video and subscribe for further quantum computing content.